Okay, this is an explanation of the Kinetics Worksheet. The first question provides some data for time and the concentration of A. You're told that it's a first order reaction. So if it's a first order reaction, we know two things about it. We know that the rate law is this, that the rate is equal to K times the concentration of A raised to the first power. And if it's first order, we also know that this formula applies to first order reactions. Okay, the question is asking for what will the concentration of A be after 40 seconds? So in the background, they're testing the tornado siren, so we're just going to ignore that and keep going. Anyway, it asks for the concentration of A after 40 seconds, but our data only gives us up to 20 seconds. So we could figure out the concentration of A at a certain time, but we do not have the rate constant. We could use this formula to figure out the rate constant and also to figure out the concentration after a certain period of time. So I'm going to pick two times. I'm going to pick from 0 to 5 seconds. The natural log of the concentration at 5 seconds, 0.14, is equal to negative K, which I don't know. My time is 5 seconds, plus the natural log of the initial concentration of A, which is 0.20. And you could do this for any 2 points. You could do 0 and 10 seconds, but you'd need to use 10 seconds as your time. You would still use the 0.2 as the initial, but you would want to use 0.1 as your final. Now when I punch this in my calculator and I solve for K, I get that K is 7.13 times 10 to the minus 2, and the units of that are S to the negative 1. Okay? Well, that's the K. It doesn't tell me the concentration of A after 40 seconds, but I can reuse this formula and say, well, the concentration of A at 40 seconds, the natural log of it, is equal to negative K, 7.13 times 10 to the minus 2, times time, which is, that's S negative 1, which is 40 seconds, plus the natural log of the initial concentration of A. Okay, and when I solve this, first I'll get the natural log of AT. The natural log of AT is negative 4.46, but that's not the answer. Because the answer that I'm looking for, I want the concentration of A. This is the natural log of it. So on your calculator, to take the inverse natural log, there's an e to the x button. It's usually the second ln button. Okay, so you'll have to take the e to the negative 4.46, whatever that number is. And that will give you the answer of 0.012 molar for number 1. Okay, number 2. Again, we are told it's first order N2O5. Okay, if it's first order N2O5, that means that the rate is equal to some constant K times the concentration of N2O5 raised to the first power. We're given the rate constant. Okay, it's 4.82 times 10 to the minus 3. And we need to calculate the rate. That's what we're looking for. And we're also given the concentration of the dinitrogen pentoxide. So to calculate the rate, we plug in the rate constant, which is 4.82 times 10 to the minus 3 S to the negative 1, times the concentration of N2O5, which is 0.0240 molar. And I get that the rate is 1.16 times 10 to the minus 4 molarity per second. Okay, number 3. Okay, we need to figure out a rate law, so it's going to be best if I write the data so you can see what I'm doing. My office door is open, so it's very likely that I will be interrupted in a moment. And then the rate is, I'm going to write it, I'm going to take it out of scientific notation. 1.113.0564. Okay, so I know I have the reaction there. So I know the rate law is going to look something like this, that rate is equal to K times the concentration of NO raised to some power times the concentration of O2 raised to some power. Okay, so to figure out what X is, I have to find two experiments where the concentration of NO changes, but oxygen doesn't. So see, I can't use 1 and 2 because the concentrations of both of them are changing. So here, 1 and 3, oxygen staying the same, but the NO is doubling. And you can see that if you say 0.0252 divided by 0.0126. You can see that it doubles. Okay, so what's happening to the rate, if I take 0.0564 and divide it by 0.0141, I get 4. Okay, so what I do with this 2 and the 4 is I say 2 raised to what power equals 4? 2 raised to the second power. So that tells me that X is 2. Okay, then I'm going to do, it's going to be a minute because I'm recording. That's okay. Then I'm going to figure out the order of oxygen. So I've got to look at two experiments where the NO stays the same, see? But oxygen doubles from experiment 3 to experiment 2. So what's happening to the rate? I would divide 0.113 divided by 0.0564, and yes, we can see that. It also doubles. So I would say 2 raised to what power gives me 2? Well, y is 1. Okay, and so that is the rate law. Computer went to sleep, so I can't see the worksheet. Okay, so that answers the first question, calculate the rate law, or write the rate law. The next one is calculate the rate constant. So what I do is I just pick an experiment. I'm going to pick experiment 1, and I just plug in the information. Okay, like the rate is 0.0141 molarity per second. I'm solving for K. My concentration of NO is 0.0126 molar. My concentration, and I got to square it, of oxygen is 0.0125 molar. Okay, and I just do my algebra to solve for K. And I will get that K is equal to 7.11 times 10 to the third. And this is overall third order, so my units are m-2, s-1. Okay. Number 4. So we're not told the reaction order, but we're given a rate constant in number 4. Okay, we're told that the rate constant is 7.0 times 10 to the 9 m-1 s-1. Okay, we can tell from the units of the rate constant that this is a second order reaction. Okay, we're told that the initial concentration of I is 0.0860 molar, and we want to know the concentration of I at some point in time, and the time is 2 minutes. Okay, now first off, I need to recognize that the rate constant's in seconds and time is in 2 minutes, so I need to convert that to seconds. Okay, so that's 120 seconds. And I'm going to use the second order formula. Okay, so 1 over the concentration of I, I'll just leave it like it is in the formula, at a certain point in time is equal to K times T plus 1 over 0.0860 molar. Okay, so I get that 1 over A is equal to 8.4 times 10 to the 11th. But see, that's not what AT is. That's the reciprocal of it. So I have to take the reciprocal of both sides. And I will get that A, or concentration of I. I'm just using A because that's how it is in the generic formula. Is 1.19 times 10 to the minus 12 molar. Okay. Then, number 5, okay, we need to write these two reactions first. Hydrogen, ICl, yields HI, and HCl. Okay, we're told this is slow. And then HI plus ICl yields I2 plus HCl. I guess I could make some effort to write neater. So we need to write a balanced equation. That's A. To write the balanced equation, I'm just going to add these two together, recognizing that the HI, since they're on opposite sides, those will cancel. That's all that cancels. So when I add these together, I've got hydrogen gas plus, I've got 2 ICLs, yields iodine gas, and 2 HCLs, hydrogen chloride gases, okay? When it asks me to identify the intermediates, okay, HI is the intermediate. It's the only one. And then C asks me for what would I expect the rate law for the overall reaction to be. Well, since what I have written in black and what you're given in the problem, that's a mechanism. So those are elementary steps. And remember that the rate law for the overall reaction will match the rate law for the slowest step. And since they're elementary steps, the rate laws follow their coefficients, a 1 on hydrogen and a 1 on HCl. Therefore, the rate law for the overall equation is rate is equal to K times the concentration of hydrogen raised to the first power times the concentration of ICl raised to the first power. And you don't have to write the 1 because it's understood. And that is the kinetics worksheet.